molecule. We've got our nicotinamide adenine dinucleotide. We'll just call it NAD so that I don't get tongue-tied. We have some type of enzyme, and we're going to see this reaction over and over again called a dehydrogenase, and they'll have special names, but it'll be something dehydrogenase, which means it's removing two hydrogens here. It puts one proton plus two electrons on the NAD molecule, and one proton gets just pumped out into the area. And so this little molecule, this little coenzyme, is going to be taking electrons and passing them down this little, I guess it's been given the name electron transport chain, because it's basically like a chain gang where you're just taking the electron and passing it down to the next molecule. But again, the whole reason we're doing this stepwise process is we don't want to just spontaneously combust our food. We can't harness energy from an explosion, but we can harness energy if we have these stepwise reactions where we just constantly move an electron from high energy to middle energy to a little less, to a little less, to a little less until it gets to its lowest energy form. Then you can harness energy at each of those steps along the way. It's much more efficient than an explosion. And the final acceptor in the electron chain is going to be our most electronegative element. Our oxygen molecule is going to be the final electron acceptor. It's our most electronegative element here. And all of that energy that gets released at each step is how we're going to generate ATP, or regenerate. So remember, we're always going back and forth, where we take ATP and we hydrolyze it to release ADP plus inorganic phosphate, and then we got to build this back together. And so to build this back together, we do cellular respiration. Pick that up. We undergo cellular respiration, and the whole process is putting the phosphate back on the ADP so that we can use it again. Seems kind of crazy, but it's how it works. Okay, and this is just pointing out the difference between an explosive reaction and cellular respiration, and why we choose this stepwise process, which seems a lot more complicated, it's a lot more involved, it's a lot more work, but we can harness the energy at each step along the process and control the process, versus here's our, liquid hydrogen plus some liquid oxygen, a little spark, you send your rocket into outer space, okay? It's a huge energetic reaction to take the electron from the hydrogen and move it to the oxygen molecule. That gives off enormous amounts of energy. It's almost unbelievable how much energy. And you think we're doing the same thing, but we're not going to outer space, thank heavens. We're able to control the amount of energy that is given off by that process because we're not hot enough to combust. Our internal body temperature, again, thank heavens, is not hot enough to provide enough energy to get over that activation barrier so that you don't have this explosion. We don't have that heat. That's the same idea of, if you had a cell and you wanted to speed up the chemical reactions, you could boil the cell, but that wouldn't be good. We can't boil our cells in our body. So we don't use heat, we use enzymes to lower that activation barrier. And so we're going to use a lot of enzymes to have a stepwise process to move electrons down the transport chain. Each time we go down a level, we give off a little energy, we harness it, and we'll find that for each molecule of glucose, we can generate about 32 molecules of ATP. So that's all we're going to do for today. We'll start in kind of jumping into the steps, and I'll